Earthman here. Today I want to talk about how to make various measurements using a transistor curve tracer. What you see here are the collector characteristic curves for a typical small signal NPN transistor. From these curves we can determine the transistor's gain and breakdown voltage and measure various other parameters. What I'm using is a Heathkit Curve Tracer. Okay, this will do a number of different semiconductors, NPN, PNP transistors, FETs, MOSFETs, triacs, diacs, diodes, just about all the different families of semiconductors that we use today. And before I go ahead and make any measurements, actual measurements, what I'd like to do is just explain what we're looking at here. Let me set this up. Okay, so what we have here is a diagram of transistor characteristic curves. And this is a typical bipolar transistor, small signal transistor. And what we see here is these are the actual collector characteristic curves. So on this axis, we have the collector emitter voltage. On this axis, we have the base current. And on this axis, we have the collector current. Okay, and then you see a diagonal line down here, which we call load line. So at this point on the curve, this is where the transistor is fully saturated and turned on. This point here is where the transistor is cut off. So it's completely turned off, no current flowing. And in between is the active region. So typically we want to bias the transistor somewhere in the middle of the active region so we still have some headroom and we're not cutting off our waveform or creating any kind of clipping or distortion. So somewhere in the middle. Okay, now what I did is I picked this point so we could easily calculate what the gain of this transistor is. So if we look at this, each of these steps is 20 microamps, okay, and that's what you saw on the scope, which I'll explain a little further, okay, but the first step is 20 microamps, then 40, then 60, then 80, okay, and on this side you see the corresponding collector current, okay, so we have 2 milliamps, 4 milliamps, 6 milliamps, etc. Now how do we calculate the gain? Okay, well, we have a formula here on the bottom, okay, and basically the gain, or the beta, sometimes called HFE, is just a ratio of the collector current and the base current. So here we have 40 microamps, okay, and for 40 microamps I have 4 milliamps of collector current. So 4 milliamps divided by 40 microamps equals 100. So the gain in this example is 100. So it's just a simple ratio between the collector current and the base current. So for example, if I had a base current of 1 milliamp and a collector current of 100 milliamps, okay, 100 divided by 1 is 100. So again, there's a simple example of where we would have a gain of 100. And this would be the DC gain. Okay, so let's go back and take a look at the display now on the scope. Okay, and what I'm testing here are two 3904 NPN transistors. I picked a transistor that a lot of us would be familiar with. So what does the curve tracer allow us to do here? Well, this particular one has two sockets, so you can do left and right, okay? So we can compare the two transistors, for example. And what you'll find is when you look at the data sheet for a transistor, you're going to find the beta value is quite wide. They're going to give you a minimum value, maybe a typical value, and then a maximum value. And you will find quite a bit of variation. They'll also list several different conditions. So you can calculate the gain with the collector current at different levels or the base current at different levels. So what I have here is I've got the curve tracer set to 10 microamps, okay, for each of these steps. So this is 0 microamps, then 10, 20, 30, 40, 50, 60, 70. Now typically we want to measure somewhere in the middle, so we don't need as many steps. Okay, that's about the middle of the active region right there. And then we can change the scaling here, okay, so that we have a little bit more sensitivity. Okay, so I went from 2 milliamps per division to 1 milliamp per division. So this gives me a little bit more resolution and makes it a little easier to measure. Okay, so what can we calculate from this? Well, if we go back to the diagram, right, we know each of these steps is 10 microamps, right? So 10, 20, 30, 40 microamps. Okay, and we're on 1 milliamp per division. So let's count the boxes here. 1 milliamp, 2, 3, 4, 5, 6, 7, 8. 8 milliamps. So how do we calculate the gain? Well, it's a simple calculation. I would take my 8 milliamps, and I'm doing this as we speak here. I got my 8 milliamps, and I'm going to divide by, what did we say? 40 microamps, right? Okay, so this is a 3904 NPN transistor, and I divide basically my 8 milliamps by my 40 microamps, and I have a gain of 200. So let's go to the spec and see what we would expect to see with this type of transistor. Okay, so here we have the specification, and here is our HFE or DC gain, which we also call beta. And we can take a look at these different conditions. Okay, and we can measure under these exact conditions, or I can measure and then approximate in between these conditions. But what you see here is the minimum value is in this column. Okay, and this is the typical value. They don't even give you a maximum value. Okay, so the condition that I'm closest to, or in between, is right here. Okay, so that can be anywhere between 70 and 300, 100 and 300. And what did we calculate? We calculated 200. So that's reasonable. Okay, so we can test the transistor to see if it's working, and we can then calculate its gain and see if it's performing in accordance to the specification. Now, if I lower the vertical sensitivity again, okay, I'm going to switch. This is a Fairchild 2N3904. I'm going to switch to another Fairchild, okay, on the right side of the tester. And if you look close, you see that the collector current is just slightly higher on this transistor. Okay, so what does that tell us? Well, the base current don't change. Okay, each step remains constant, right? So 10, 20, 30, 40 microamps. But you see the collector current, right, goes up slightly. All right, this would be basically a slight increase. So this particular transistor has a little bit higher gain, okay, than the one we're using as our baseline. Okay, not bad. So let's take another Fairchild transistor, okay, and let's plug that in the socket. Let's compare this one. What do you see there? You see that for the same transistor, same manufacturer, the gain is actually much lower, right? So let me change the resolution back so we get a little bit more accuracy in the measurement. But what do we have now? You can actually see a dramatic difference between these two. And again, they're both Fairchild. They're both the same manufacturer. Okay, the variation is caused by the doping process and the concentration of semiconductor material, which is not accurately controlled the way you might think. You know, they grow these crystals during the doping process, and they can dope with boron, for example, but they don't have absolute control over the process. So what they do is they test the transistors and see if they're within a certain range, and that would be considered acceptable. Okay, so here, this is our baseline. Okay, you can see, for 40 microamps that the collector current is high, and here for 40 microamps. Well, let's measure it. Okay, I'm now on 1, 2, 3, 4, 5. I'll call it. Let's just call it 5.5, just to round it off. So now if I do the calculation, right, I'm at 5.5 milliamps, and I still have my same 40 microamps, but now my gain is only 137.5. Let's call it 138. So you can see that even between transistors produced by the same manufacturer, you see quite a bit of variation. Okay, let's go back to our baseline again. We'll change the resolution here. Now I got another 3904. Okay, and this particular one is from Motorola. Okay, and we'll see how that compares. Now you might ask yourself, well, what's the advantage of this? Well, let's say in certain applications like a push-pull amplifier, you want the transistors to be working together, working in unison, and you want them to each be handling the load the same way. Otherwise, one's going to be a higher current, the other one's going to be a lower current, and you might see a temperature gradient between the two transistors. So what you can do here is you can just basically sample the collector characteristic curves and match two transistors that have a similar gain. And actually the first two transistors that I measured were pretty good. Okay, so now I've got the baseline Fairchild transistor, and we're going to take a look at the Motorola. You can see once again that this is also a 3904, but you can see that the gain here is also much lower, right? Our base current doesn't change, but the collector current changes quite a bit. Okay, so you can see it's dropping by, now I'm on 2 milliamps per division, so it's dropping by 2. Okay, let's call that like 20% difference. Okay, so that's basically how to calculate or measure the gain of a transistor, and how to compare different transistors either between the same manufacturer or different manufacturers. I'm back to my baseline transistor again. Another measurement that you could make very easily is the breakdown, secondary breakdown voltage. Okay, and what we do there is, now remember this axis is my collector emitter voltage, right? And if we check the spec, which I'll go back to in a minute, we see that the breakdown voltage is rated at 40 volts. So now I'm at 10 volts per division. Yeah, let me change that to 5. It might be a little easier to see it with a little more resolution. Okay, right there where you see that knee, okay, that's the breakdown point. And actually, if I went any further, this transistor would really heat up, and you could damage the transistor depending on the amount of voltage you apply. This particular curve tracer does limit the voltage, but you can go up to 200 volts with this particular one, and a fair amount of current as well. So I'm going to call it like right there is where I see the knee start to take off. Okay, and I changed the resolution, so basically now we're at 5 volts, right? This is the collector emitter voltage. So 5, 10, 15, 20, 25, 30, 35, yeah, call it 40 volts. And that's the breakdown voltage. So if we go, for example, back to the spec, we would see that our breakdown voltage, okay, let's swing this over. Okay, and take a look here. Okay, so this is collector emitter breakdown, and you see it's rated for 40 volts. So after the 40 volts, yeah, you're out of the safe operating area, and you could damage the transistor. So that's a quick look at some small signal transistors and how to compare transistors, how to measure the beta value, and how to measure the collector emitter breakdown voltage. We're going to go ahead now and take a look at a power transistor and then an RF transistor, a 2SC 2879. Okay, so now I'm back. What we're looking at this time is a power transistor. It's a 2SC 3150. These particular transistors don't have as much gain as, say, a small signal transistor. So let's first take a look at the setup here. Okay, I'm testing the transistor with a set of leads. And if we go over to the specification and we look at the gain, we would see the gain is going to be somewhere between 10 and 40. So let's go back to the display here and see what we actually measure. Incidentally, this is called looping. Okay, this depends on the amount of capacitance that the transistor has. The input capacitance as well as the output capacitance, and there is a loop adjustment on this particular analyzer. Sometimes it helps, and yeah, that's not bad. We can bring it back together. So that's basically caused by the parasitic capacitance of the transistor. Okay, so now this time I've got the base set to 50 microamps. So we have 50, 100, 150, 200, right? 4 steps times 50, 200 microamps. And then we've got the vertical sensitivity set to 0.5 milliamps. So 0.5, 1, 1.5, 2, 2.5, 3, 3.5. Okay, so some quick arithmetic here. 3.5 milliamps divided by 200 microamps, I'm looking at 17.5. Okay, and what did the spec say? Somewhere between 10 and 40. So it's reasonable. One thing to point out here that you can see in the baseline transistor that we had even spacing between each of these steps. Okay, showing that it was very linear, right? For a specific value of base current, we had a specific value of collector current. Okay, you can see here that the distance between these steps is not exactly the same. So this device is not as linear. So there's another measurement that you could make. There are more accurate ways, but I just wanted to point that out, that you can see the differences in linearity. Okay, next we're going to take a look at a Toshiba 2SC 2879. Okay, so now I'm back. This time we're taking a look at the Toshiba 2SC 2879. So that's what the collector characteristic curves look like. This particular component has a pretty high amount of input capacitance and output capacitance, so you see the looping effect there, which is pretty common. You can kind of compensate here. It's about as good as I can get it. Okay, so this is the setup that I have. I had to fabricate a fixture here so that I could securely connect to the tabs and make a good measurement. I did a before and after with just a component to see if the fixture had any effect on the looping or on the parasitics. It does not. So this fixture allows me to just do a quick changeover to compare devices. And if we take a look at the specification again, we're going to look at the DC gain. Okay, so you see quite a bit of variation. Minimum is 10, maximum is 150. Okay, and also with RF transistors, they also give you the power gain, okay, which is GP, okay, and this is basically the AC gain, and they'll normally specify the parameters that they use. So this particular one was tested at 28 megahertz and 100 watts PEP. Okay, so that's basically it. And the maximum collector emitter, BR means breakdown. These devices are rated for 18 volts. You can see right here, this is VBR ECO, which is the collector emitter breakdown voltage. So you shouldn't run these past 18 volts, although some guys do. You're basically out of the safe operating area at that point. Okay, so let's go back now and look at the curves here. Okay, so I've got the steps for the base voltage set to, once again, 50 microamps. So 50, 100, 150, 200 microamps here. And then I've got the sensitivity for the collector current at 1 milliamp per division. So 1, 2, 3, 4, 5, 6, call it 6.5. Okay, so if we calculate 6.5 milliamps divided by 200 microamps, coming up with 32.5 for the DC gain or the beta value. And that's basically what these small testers provide. Some of you, if I can get this in the view of the camera, some of you might have a tester like this one. Okay, this typically gives you the beta value. Obviously, it can only test at very low levels. My particular curve tracer can test up to 200 volts, but that also gives you the DC beta value. You can calculate the gain as well with this instrument. It's a little bit more complex. I'm not going to go into that today, but there is a procedure in their manual. So it said we should be somewhere between 10 and 150. We're at 32.5. There is a lot of variation in these devices, so and a pretty wide range for beta. So that's why it's important, again, for a push-pull design to match these transistors so that they're each doing the same amount of work, conducting the same amount of current, to kind of share the load. And as I mentioned, the breakdown voltage is about 18 volts. So let's take a look at that. Here I'm about, let's see, 2 volts per division. So let's go up, and I see the curve. I see the knee somewhere around here. So 2, 4, 6, 8, 10, 12, 14, 16. Yeah, about 18 volts. And that's where you start going out of the safe operating area with this device. So that was a quick overview. We took a look at a small signal NPN transistor, and we compared different transistors, the same manufacturer and different manufacturer. Found some interesting results there. Looked at a power transistor and looked also at a Toshiba 2SC2879 RF transistor. So I hope this was helpful. If you have any questions, please feel free to ask me. RF Man, thanks.